All right. Thank you, Max. Thank you, Oliver, Chris, and Leo for being on my committee. And thank you, everyone who's here to listen to me on my PhD speaking qualifier. I'm Shivam Vats, and I'll be talking about my work on plan to minimize human and robot efforts over tasks. This was joint work with my advisors, Max and Oliver. In 1961, when Heinrich Ernst did what was probably the first PhD thesis on autonomous robotic manipulation, he imagined a future in which robots take over most of our tasks. And he made a point to show a video of himself doing nothing just to stress on that point. In 2021, we have robots which are much better in terms of hardware, and we expect them to do a large variety of tasks. This is in contrast to robots earlier, which could only do a specialized task at one time. And this means that we want robots which can learn a versatile number of skills and can adapt to changing circumstances. But what these two videos do not show you is what happens before a robot is capable of doing any of those tasks. A very popular approach of programming robots is via human demonstrations. Here, my friend Kevin is teaching this Franca robot on how to cut a cucumber. He had to provide 10 demonstrations before the Franca was able to learn these skills. Here's another video of a researcher teaching a robot on how to wipe table. And they had to provide almost 1,000 demonstrations for different types of material to be wiped before the robot was able to wipe the table. Looking at these videos, it's hard not to observe that often providing these demonstrations can be a lot of work. The demonstrator first needs to figure out what's the right strategy for the robot, set up an experimental setup to capture those demonstrations, and finally provide those demonstrations manually each time. Often in practice, the number of demonstrations that a teacher provides is determined in an ad hoc way. For example, in the previous two videos, the numbers were 10 and 1,000, which are round numbers. In contrast, human execution is very easy, fluid, and natural, and we don't really need to think too much about it. Which begs the question, why do we even care about teaching a robot? The obvious answer to that question is that it is going to save human effort in the long run. And even though the upfront cost of teaching a robot is high, that is going to be paid off eventually when the robot performs similar tasks autonomously. However, in many domains, the task distribution can change suddenly. And this assumption that the cost of teaching will be paid off may not hold. So let's take a case study of a food processing plant, which gets a few orders of frying things, let's say making pancakes, of cutting tomatoes and squeezing grapes. And the managers of the plant train their robots to achieve all these tasks really well. However, on day 2, the task requirements have changed, and instead of cutting tomatoes, the factory needs to cut carrots. Instead of squeezing grapes, the factory needs to squeeze limes. All the effort that went into teaching the robots on day 1 is suddenly of no use anymore. And which just goes on to show that if the task distribution is changing, teaching robots all the skills that you can is not always a great idea. This is an observation that has also been made in economics, where people often focus on long-term consequences and they take decisions based on those, disregarding the short-term pains that they may have to incur. If you noticed in the previous two examples, not only is the kind of task that the robot needs to do important, it's also important how many of these tasks the robot needs to perform. So in the rest of the talk, the representation I'm going to assume for tasks is a discrete representation, by which we mean that the robot knows ahead of time what is the sequence of tasks it needs to perform. And this is motivated by factories, which often know their orders for the next few days or weeks, but may not know or may not be able to predict the requirements much later. Now let's try to conduct a thought experiment to understand when it makes sense to teach a robot and when it doesn't. Suppose you need to make 1,000 pancakes, and you have a robot which you can program to help you make those pancakes. This is a classic case where automation makes sense because no one wants to make 1,000 pancakes. And hence, in this case, we would say that automating this task makes sense. On the other hand, if you just had a single pancake to make, the cost of teaching the robot is much higher. And hence here, it is preferable to have the human do this task. So that is the crux of our work, which is we want to teach a robot only if it helps you achieve your tasks faster. To summarize what we have seen so far, suppose you have a set of tasks, which is represented by this blue circle. Using classic online learning, you would use some of these tasks as training tasks to teach the robot so that the robot can autonomously solve the remaining tasks. In contrast, through these examples, what I've tried to show you is that if you're focusing on only these tasks, which is represented by this blue circle, it is often less effort overall to delegate some of the tasks to the human and not have to train the robot on how to do those tasks. You can imagine that these tasks could be outlier or which are difficult to train to the robot. Now, of course, this question has been looked at in different ways in prior work. In particular, our work falls in the category of shared autonomy, where control is switching between human and a robot. The closest work to ours is by Richter et al., who learned controllers by minimizing human effort. But the goal there as well was to eventually achieve fully autonomous behavior. In contrast, in our case, we are only focusing on achieving a set of tasks, and we don't really care as much whether these tasks are done by a robot or a human. There is also other work in shared autonomy by Chernova et al., who learned policies from human demonstrations, and the goal there was the robot should focus queries when it is uncertain, in the hope that this will minimize the number of human demonstrations. And there is other work as well, which looks at semi-autonomous MDPs, and where the control is switching between a robot and a human, but the focus there is on modeling the human. Another related field is active learning, which looks at how do you minimize the number of samples to learn a machine learning model faster and better. And there is a lot of interest in the robotics community in incorporating those active learning ideas in skill learning. And there has been a whole sequence of works which try to do that. In particular, they try to learn contextual policies which can adapt to different tasks. And these contextual policies are learned using active learning. Some of these works also focus on learning policies or skills for a given task distribution. But again, the goal is to achieve full autonomy, and which can often be rather expensive. Right. So in contrast, our work focuses on achieving a set of tasks with minimal effort, and we are going to specify what we mean by effort later on. Finally, all these works propose some sort of greedy approach where we're trying to greedily minimize some notion of cost. In contrast, our work is a planning-based approach, which means we can talk about the suboptimality, the global bounds on the solution quality. All right. So let's try to set the problem up first. We have two agents that we're going to model. The first is a robot on the left, which maintains a library of skills represented by the letter L. On the right, we have a human who we assume that can solve all the tasks if need be, and it does so at a fixed cost for every time it needs to solve the task. Now we consider a sequence of tasks that need to be solved, in this case, frying tasks. And the question is, should the robot be taught a frying skill or not? In this case, because there are a lot of frying tasks, so let's say that the robot needs to be taught this frying task, and then this frying skill gets added to the library of skills that the robot has. Of course, we're interested in what happens when the task distribution changes. So imagine the factory gets different kinds of tasks. So now it has to do a lot of cutting tasks instead of just frying, which poses the question, should the robot be taught these two skills which are required to cut a carrot and to cut a tomato? And our work tries to come up with a principled answer to that question. Right. So the first step of our approach is to formulate this problem as a Markov decision process. The state in our MDP represents or captures the library of skills that the robot has, here represented by L, and the number of tasks that it already has solved. So that is I. The first option that we consider is to let the robot execute the task, here represented by A sub rob, which incurs a fixed cost C sub rob. And of course, the robot may either succeed or fail. If it succeeds, that's great news. The system can move on to a different task. While if it fails, we assume that the human has to intervene to fix that situation, which incurs a higher additional cost. The second option is to let the human do the task. Because of our assumption, the human always succeeds, but this incurs a higher cost C sub human. And finally, if the system believes that this is a task which is going to be seen frequently later on, it would make sense to provide a demonstration to the robot so that it can achieve that task autonomously later on. And this is represented here by the action A sub demo, incurring a potentially much higher cost C sub demo. But this also updates the robot's library by adding a new skill pi, which is specific to that particular task. Now, an interesting thing to note here is that the probability of success of a robot on any task depends on the skills it has learned on previous tasks. So there is a tight coupling between the skills that the robot learns and the probability of success later on future tasks. It turns out that we can slightly simplify this MDP by taking an expectation over the success and failure of the robot, which gives us this one-step MDP where we have 3 actions and 3 costs. Interestingly, the first cost, that is the cost of the robot executing the task, is dependent on the probability of failure, which is also a function of the skill library that the robot already has. Now, this is just the one-step MDP. To get the full search tree, you need to apply these actions at every state, which is going to give you the full problem to be solved. So here we applied the 3 actions at every state. Now, the problem here is that the resulting tree is exponential in the number of tasks because you're applying 3 actions at every state. And even with 30 tasks, this graph is too big to be solved by graph search. This is bad news because we would want to be able to solve this problem for hundreds, if not thousands of tasks, because factories get the number of tasks that factories gets is of that order. So how do we go about simplifying this problem so that it can be solved in a tractable way? This brings us to the first contribution of our work, which is an efficient representation of this problem, which also leads us to an efficient solution to this problem. Before we get into the planner proposed by us, we need to look at a different perspective at this problem. So suppose you have a set of tasks. You have some cutting tasks, you have some frying tasks. Even though these tasks look quite different, there is a lot of structure within them. For example, you can imagine that the cutting tasks are more closely related to other cutting tasks, whereas the frying task is quite different from those. Even within those cutting tasks, cutting a tomato is quite different from cutting a carrot, but it is more similar to cutting a capsicum. And hence, if you look at these circles, which represent a skill, you can imagine that if you had a skill to cut a carrot, it will not be able to generalize over tomatoes. However, if you had a skill represented by the red oval here to cut a tomato, there is a strong likelihood that it may generalize to the capsicum. So this is what we mean by the coverage of a skill. We say a skill covers a task if it is able to solve it. And these different ovals correspond to different skills. All right. Now we'll look at a specific example to understand how we can convert our original problem in this representation. So in this example, we have 4 cutting tasks. As I said before, cutting a carrot is quite different. So it's if you know how to cut a carrot, you can't really cut tomatoes or capsicums. On the other hand, if you can cut a tomato, which is represented by the red oval here, there's a strong likelihood that you can cut the capsicum. Imagine that we have the costs for all the different actions that we considered that's given to us. So the cost of robot execution is 10, but the cost of human intervention is 10 times that, whereas the cost of a human demonstration is much more, that's 15 times the cost of robot execution. And the question is, which skills should be learned by the robot and where should the human intervene? Just looking at this problem, we can actually come up with the optimal solution, which would be we'll teach the robot this tomato cutting skill because it allows it to solve a lot more tasks. But on the other hand, we don't teach the robot a carrot cutting skill because it does not really generalize over the remaining tasks. So the optimal solution here is to get a demonstration on the first task, a human intervention on the second task, and the remaining two tasks can be solved by the demonstration that the robot received on the first task. The interesting thing to note here is that even though there were potentially three different skills which could be learned, we only had to learn one skill to be able to achieve all of these tasks in the least cost way. All right. So this specific problem is actually a very standard computer science problem, which goes by the name of set cover problem. The set cover problem considers a set of elements which need to be covered. In our case, each element is a task, and by coverage, we mean that that task needs to be solved. Secondly, in the set cover problem, we require a collection of sets, and each set covers some of these tasks. So in our case, it would correspond to skills where each skill can cover some of the tasks. And finally, we have cost for each set. And in our domain, the cost is specified by the user, which corresponds to what's the cost of providing a demonstration, what's the cost of human intervention. The set cover problem is to come up with the least cost collection of sets that covers all the elements. In other words, the problem is to come up with skills or human demonstrations that allow the robot and human to solve all the tasks so that the total cost of this assignment is minimized. In this case, you can cover all of these 4 tasks using just 2 sets, and that's the minimal cost representation of this problem. The first result of our work is that we can reduce the original MDP that I described earlier to a set cover problem. And the way we are doing to that is the following. Imagine you have a set of tasks which need to be done. We are going to make the observation that if a human attempts a task once, that's the only task it can solve. So if I ask the human to cut a capsicum, it can't solve any other task. To solve any other task, it would have to do the execution again and incur additional cost. So we are going to introduce sets which are singletons corresponding to human execution for each of these tasks. That gives us 4 sets corresponding to human intervention, and each of these costs C sub hum. On the other hand, if you teach a robot, it allows it to potentially cover multiple tasks. So if I were to teach a robot how to cut a capsicum, it potentially allows the robot to cut a tomato. And in that sense, that demonstration is more beneficial than just asking a human to do it. Similarly, we'll have these sets for all these tasks, but these demonstrations are much more expensive than a human intervention, and hence they cost C sub demo. Now that we have this set cover problem that we have set up for our original cost minimization problem, we can solve this using integer programming. Integer programming is a popular way to solve set cover problems, so we have existing tools which solve this problem really well. In particular, if you look at the objective here, the goal here is to minimize the overall cost of human intervention and human demonstrations. We introduce binary decision variables, each of which correspond to either the human executing the task or it providing a demonstration. So X sub I is 1 if the human is providing a demonstration on the ith task, while Y sub I is 1 if a demonstration is to be provided. The objective is to minimize the overall cost, and the fact that every task needs to be solved is added as a constraint to this integer program. Right. So why is this a good solution? Now, first of all, compared to the MDP formulation that we looked at earlier, this only has a linear number of decision variables. In contrast, the graph that we built earlier had an exponential number of states in the number of tasks that you want to solve. Secondly, as I said earlier, there are off-the-shelf solvers which we can use, and these solvers can handle millions of decision variables, meaning we can solve for hundreds of thousands of tasks if we desire to do that. And finally, many of these solvers use techniques which can give you bounds on the solution quality, and which is great because we know how good we are doing and whether there is a need to further optimize the solution or not. So far, we have been assuming that we have these crisp sets which tell you whether or not a skill can solve a task. So here in this case, I'm assuming that if I have a skill for cutting a carrot, I know for sure that it's not going to work on any other task in this task set. On the other hand, reality is rather probabilistic. So if you have a skill for cutting a carrot, there is some probability, which could be non-zero, that it might be able to work on cutting a tomato or a capsicum. However, our planner, which we proposed, can only deal with these discrete sets. So, for example, there is some probability that the tomato task is going to succeed, given that the robot has seen some demonstration on cutting a pepper. And the question is, how do we adapt our approach to handle these probabilities, which are more likely to be found in the real world? So a common approach to handle probabilities and to convert from probabilities to binary labels is to threshold them. So if you have a probability P and a threshold theta, you could, for example, say that if the probability is less than theta, the label is 0. And if it's more than theta, then it's 1. And so for a given theta, you can convert your probabilities into these discrete sets, which we can then handle using our set cover approach. However, it's not clear a priori what is the right threshold that should be chosen for this task. To deal with this, we propose a simple approach, which we call the IMSET cover, which does a search over different thresholds to identify a plan which works the best. This consists of 2 steps, which are done in an iterative way. So the IMSET cover planner first picks a threshold, thresholds the probability distribution that it has, and converts them to binary labels. That gives it the set cover problem that it can solve using integer programming. And then the resulting plan is evaluated using actual probabilities, which tells you actually how good that plan is. These 2 steps are repeated iteratively until it has exhausted all the threshold hypotheses, and the planner returns the best solution it has found so far. All right, so this brings us to the end of our first contribution, which was this planner. If I can take any quick questions at this point.
How do you know what's the probability associated with the skill succeeding or failing given another skill?
Yeah, so that's exactly what I'm going to talk about next, which is the precondition prediction model.
Okay.
Cool. All right, so where do these probabilities come from, right? We have talked about 2 different representations of the planning problem, and we have come up with a great planner which can solve that. But we haven't really talked about where we're getting these probabilities from. So before I get into how we get those probabilities, let's look at this example. Imagine you have a carrot to cut and a tomato. And the question I ask you, it is, what is the probability that you'll be able to cut a tomato after I have shown you how to cut a carrot? So if I had shown you how to cut a carrot, and if I had taught you a skill for that, you could simply execute that skill on cutting a tomato and you'd know the answer. But we are trying to answer this question even before we have seen that demonstration. So let's look at the features of these tasks in particular. The carrot is firm and conical. In contrast, the tomato is very mushy and spherical. So if you try to imagine what kind of a policy you would get to cut a carrot, it's probably going to apply a lot of force to be able to go through the firm texture of the carrot. On the other hand, a tomato is very mushy, so you want to be soft and delicate so as not to crush the tomato. And based just on these features, you can probably guess that if you know how to cut a carrot, that demonstration is not going to transfer directly to a tomato. So the probability of success on a tomato task is low if you have only seen a carrot cutting task. And that's the insight that we use in our preconditions prediction model, which is that you can make this prediction of success of a demonstration just based on the features of the task you are receiving that demonstration on. So here we have a model which we represent by the letter M, and it takes in the features of the task on which it is going to receive a demonstration. So phi1 is the features of a carrot, which is going to be firm and conical. And it also takes in the features of the task on which you desire to evaluate this skill, which is a tomato, so mushy and spherical. And the model outputs the probability that the tomato is going to be achieved by a demonstration from the carrot task. Intuitively, you can imagine that what's going on inside this model is that it's comparing the features of these two tasks, and it is asking the question, are these two tasks similar? And if these two tasks are similar, then it's likely that the demonstration is going to transfer, otherwise not. This is exactly a binary classification problem, which is how we pose this in our work. And we train this on data which we generate in simulation. So we don't want to use actual human demonstrations because clearly that's expensive, and we're trying to avoid that. Right. So the training is very simple. We assume we have access to a simulator. Here we use Isaac Gym. And we sample a bunch of tasks from a task distribution. So let that task be represented by features phi1. We train a policy for that task in simulation using reinforcement learning, and evaluate that policy on a bunch of other tasks to try to understand what kind of tasks can be solved by the policy. This gives us features phi1, where the task was learned, and phi2, where this policy was evaluated. Note that our model takes both these features, and hence we saved these two features. Finally, the output of this feature is whether or not that policy succeeded. And that's the target that we're going to optimize for in our classifier. So at this point, I'd like to summarize the whole framework that we are proposing. The first step is to do some offline training and simulation, where we train this precondition prediction model, which tells you what is the probability of success on a task B if you get a demonstration on task A. At test time, this precondition prediction model is used by our set cover planner, which comes up with a plan which is optimized for the given sequence of actions. And based on this sequence of tasks, and based on this sequence of tasks, it either asks the human to do it, or provide a demonstration to the robot, or asks the robot to do the task. That brings us to the end of our second contribution. Now I'm going to get into evaluations that we did in simulation and real world of our work. So the domain that we chose for our experimental evaluation is robust block insertion under uncertainty. So there is a slot which is at the corner of this, and this block which is in the gripper needs to be inserted in that slot. The problem here, of course, is that the location of the slot is not known accurately. So if you were to directly try to go down, you would not be able to make the insertion. On the other hand, we assume that we have a model of this task known beforehand. So for example, we know that there are walls next to the slot. And a good skill is one, a robust skill is one which leverages these walls to localize the block and make the insertion. So here, if you look at this policy, what it is doing is it's first moving towards the wall so that it knows that it's right next to the wall, and it has reduced the uncertainty along one direction, and then it moves along the other direction to do the insertion. In these experiments, we try to come up with these policies which make the insertion robust. So to understand why this is a difficult task, let's consider two tasks where the location of the slot is different. If you look at task A, the slot is right next to wall 1. So if you want to do a robust insertion, you need to first move towards wall 1 and then make the insertion. On the other hand, if you go to task B, the position of the wall is flipped. So in this case, you need to move to the right towards wall 2 to make the insertion. And clearly, depending on the location of the slot and the walls, the right skill changes. Hence, in this case, we parameterize each task by the location of the slot and the location of the walls in the task. We compare our planning-based approach against 3 baselines. The greedy planner approach makes use of the precondition prediction model that we trained earlier. However, instead of planning over the full horizon, it greedily picks up the best action by evaluating the consequence of that action over all the future tasks. We also have 2 baselines which do not make use of this prediction model. So if you don't know the prediction model, it's really hard to choose between asking for a demonstration or asking for a human to intervene. So baseline 1 simply asks for a demonstration if the robot is not confident of doing a task. And baseline 2 has a fixed budget of demos because baseline 1 can ask too many demonstrations. So we give a fixed budget of demonstrations to baseline 2, after which it shifts to asking human executions. Here are the results. So the first row is our planner MSET cover, and we are evaluating all the different planning approaches in terms of the total cost, which is the sum of human and robot effort. And we are also looking at the number of demonstrations and number of human interventions that were required by each approach. So the first result is, of course, that our approach outperforms all the alternative approaches. In particular, if you don't use a precondition prediction model, then you can do much worse. However, if you have a precondition prediction model, for example, Greedy has the precondition prediction model, then that outperforms the other baselines. However, Greedy can often take suboptimal decisions, which are rectified by our planning-based approach. So how does our planner reduce the total effort to accomplish these tasks? The key here is that it minimizes the number of demonstrations. So in our framework, the cost of a demonstration is the highest. For example, in this experiment, we assume that it is 300. And our planning-based approach minimizes the number of these demonstrations, which leads to overall less effort. However, it does this at a cost of asking for more human interventions. So if you compare it with the greedy approach asks for fewer human interventions, but as a result of that, it needs to ask for more demonstrations, which shows that our planning approach is able to reason between providing human demonstrations and asking for human interventions, which leads to overall less cost. So the results that I show you assume a fixed cost of human demonstration, which is 300. Now, the behavior of the planner, of course, changes as the cost of a demonstration changes with respect to a human intervention. So if the cost of a human demonstration is the same as that of a human intervention, then the minimal cost strategy is to always ask for a demonstration, because with a demonstration, there's always a possibility that you can solve a few more tasks. On the other hand, if the cost of a demonstration is much higher than that of a human intervention, then in terms of cost, it always makes sense to ask for human execution. And this is kind of a spectrum. So as you go from left to right, you'll see fewer and fewer demonstrations being asked. The planner would focus on demonstrations which actually allow the robot to cover a large number of tasks. So we also performed this experiment in the real world. And here I'm just showing you one example of the plan under execution for a peg insertion task. So this is the same task as the block insertion task, but with the difference being that here we are inserting pegs in a hole and not blocks in a slot. But the goal is still the same. You have to first move towards a nearby wall to localize the position of the robot. And then you know the position of the hole with respect to that wall. So you move by that amount. Here the robot is executing a demonstration it received on a different task. And you'll see that it's going to succeed. All right. So of course, we proposed a way to minimize cost in robot and human costs, but there are a number of limitations that still remain. For example, we assume a fixed cost of robot teaching. We don't assume any transfer among skills, so we have this library of skills which is not sharing information among each other. We require a common feature space to describe all the tasks, because our precondition prediction model has a fixed input vector space. And finally, of course, we require a trained precondition model, which can sometimes be expensive to train. Our feature work is motivated by these limitations. In particular, we can estimate the cost of human demonstrations using simulation data. So you can imagine that if a skill is hard to learn using reinforcement learning and simulation, it's probable that that demonstration is going to be expensive. We would also like to model transfer among skills. So here we assume that each skill is its own thing and it gets trained only once. Instead, what we want to look at is how can we retrain skills, or how does training skill A affect skill B? Third, here we had to hand design a feature space to represent tasks. It would be interesting to look at whether we can learn a common representation for a diverse set of tasks. And finally, instead of requiring a trained precondition prediction model, it would be interesting to see what we can do with an imperfect model and update it online as the robot receives more and more human demonstrations. So that brings me to the end of my talk. I'll be happy to take any questions.
All right, thank you very much. I'm gonna clap in the solitude, but anyway, thank you so much. So the kind of the process is that the committee first asks questions, and then everybody else in the audience can go ask questions. So we're going to start with the committee, and particularly, I think a typical order is that a student would go first, unless a student doesn't want to go first. So Leo, are you okay going first?
Yeah, I'm happy to ask a question.
Okay, great. Go for it.
Yes, I have a couple of questions. You're just gonna have to see how many I want to actually ask. So my first question is, in your one-step MDP,
right?
Do you think it makes any sense to introduce some sort of reward for robot failure? So for example, in your case, you're using reinforcement learning, and when your robot fails, you assume that there's never really any benefit to that, right? It just ends up producing extra costs because the human has to do it. But there is some sort of intrinsic benefit to robot failures in that they can aid learning, right? So yeah, in this case, if you fail, then the human does it, nothing happens. But in real life, failures are valuable, right? At least I tend to think failure is valuable in that then you could use that as a sample to your RL algorithm to sort of improve your results. So I'm wondering if if it'd be possible to incorporate some sort of value into that failure branch, which helps your preconditioner, or some notion that maybe failures would help your preconditioner and raise your probabilities, if that would still work in your formulation.
Right. So that's a great question. Here, what we're doing is we are not really using that information in any way. The only place where the robot's model, the robot skills gets updated is this action where you provide a new demonstration, but we are disregarding the observation that we get here. Now, we did that for a simple reason, which is that it is just a single observation, right? And we thought that that's not going to change the model a lot. And hence it was a reasonable assumption to just ignore that, because if you try to model that, then that's going to complicate this MDP even more. So the question is, what's the additional benefit that it gives you, and whether that's useful to model or not.
Okay, yeah. So I have another question, which is, you propose this imp set cover algorithm, and it's interesting because it kind of makes you have more of like a soft set cover algorithm instead of a hard set cover. Do you have any sort of bounds for the time complexity of this, sort of the suboptimality of this, sort of how it might compare to other formulations of a soft set cover problem?
Right. So So the basic set cover problem, which is here, which we solve here, this is, of course, you can solve this optimally, or you can get the bounds on this. Natively, you're like, if you just take and max over those solutions, then that's not going to give you a bound. However, in the paper, we also compared the solution of this planner with a greedy approach, and we took the max versus the greedy approach. So it turns out that if you run a greedy greedy planner to this problem, it is going to be right most of the time, and it is going to make mistakes in certain situations. And the idea that we have is that you want to switch over to this planning-based approach wherever you think that the greedy approach can make a mistake. And we were able to show that this planner will do better than the greedy approach, at least. However, in terms of comparison with the global optimality, at least so far, we have not been able to say anything.
Okay. Okay, that's fair. That's interesting to give a baseline there. Another question is, do you think your approach would be amenable to adding uncertainties to your costs. So instead of them being a scalar value, that you instead have a distribution over how much time a demonstration or robot might take, right? Or does it not matter because the means are going to be the only thing that matters?
Right. So I sort of alluded to that in the future work section where I said that it is possible to instead of taking a fixed cost of demonstration, you can have costs which are actually a function of the task that needs to be solved. So imagine if you have different kinds of tasks, each of them can have different cost of demonstrations depending on what the task is. But even there, at least in this framework, we assume that it's a point value, it's a point estimate. It's not a distribution. And if you assume a distribution, then it's just going to make this graph more intractable. And the question is it really worth it? Where do you get those distributions from? Yeah, I don't see how it would directly be solved by the set cover approach. I'll have to think about it.
Okay. Yeah, well, I say you can empirically get the distributions, right? I mean, you have human trials, you have robot trials, right? You have demos. You know that that whatever the trials are, they're not always a fixed cost. They are a distribution. My last question, I swear it's my last question, is used RL for your preconditioner. You built a reinforcement learning algorithm.
Right.
And then you have this empirical relationship between how similar tasks are. I'm wondering if you think there's any value in using a different type of model like ILQR or DDPG, or let's say ILQR, and potentially getting uncertainty mismatch in terms of some sort of analytical function, right? You might, if you do ILQR, you'll have dynamics functions and you'll be able to compare how similar they are. And this will be an analytical question about how similar tasks are and not an empirical one, as in your case. Do you think there's any value in maybe simpler models for learning, which would actually give you more analytical bounds for similarity?
Right. So one key step of our precondition prediction training is that you can't really have an arbitrary function which you're trying to learn using RL. So it has to have some parameterization, and you're learning the weights of that policy using RL. And if you have a policy class which is, let's say, very large, then you can potentially have many different kinds of solutions. So I agree that having a simpler policy representation like ILQR, that's going to make this comparison much more solid.
All right, thank you. Yeah, those are it.
Yep, thank you.
All right, thank you very much, Leo. All right, let's see if Chris has any questions. Chris, are you okay going next?
I'm pressing buttons.
Oh, okay.
Buttons.
I thought for a second you didn't have any questions.
Sorry.
I know.
Okay. I think this is a very useful step forward to getting robots to think about a multiplicity of ways to do things. So that leads me to want to massively scale this up and include, I agree with Leo, you would want to think about all sorts of things, including just generally asking for help from humans or figuring out how to ask specific questions. You also want to learn which human teachers are actually good, so you ask for the right teacher. And at some point, the robot decides what it wants to do and whether to start the robot revolution and kill all the humans. So that should be in there somewhere as well. Once you've said that, you start asking the question, well, who else is thinking about, when to ask for help? And, there's a huge literature on dialogue management and getting, very soon the Amazon stuff and the Apple Siri stuff will start having long-term conversations with you over time and have goals. So how do you relate this to dialogue management and those kinds of things? And how do you scale up massively?
So just to understand what you mean by a dialogue better, is it just a robot talking to a human, an AI agent talking to a human?
Or to another robot or basically it boils down to You treat the dialogue as a task. The agent has some goals, and it does what you do in terms of it figures out the best way to achieve the task. And sometimes that involves asking the human for help or explanation. And sometimes it involves asking the human for assistance or even to do it for them. Manuel Veloso had robots running around, I believe, that would ask humans to press the elevator buttons.
Right, right. So I agree with you. This is a problem that has been looked by a lot of people. In particular, a lot of focus has been on minimizing the number of human queries because, as you'd expect, these demonstrations are expensive. So a lot of focus has been on that. I think what's unique in our work is that we have this notion of minimizing the overall cost, which sort of grounds the goal and which you can ascribe a cost to, right? So often what the goal is not well defined, and what we do here is that we give you a very well defined goal to be achieved, which you can like you can give it a cost and say, okay, all right, that's the cost of this plan. And I feel like that's the primary contribution of our work. Now, when you compare it with dialogues,
I wouldn't agree with that statement that it's either unique, that it's unique to your work. That's a very common framework.
okay, I see. Well, I mean that's the focus of our work at least.
Right.
Right. So when you compare it with something like a dialogue, it's not clear to me what's the overall goal and how do you quantify how much you've achieved that goal. So
Yeah, that's what huge amounts of money are being thrown at trying to answer. Because whoever gets that to work well first is going to capture the market of all these Echoes and Google Homes and all this other stuff. There's a lot of money in those hills.
yes, I suppose a lot of work is going to figure out, the parameters of this problem. So, what's the cost of demonstration, like Leo said, what are you'll have to adapt this framework to different tasks. So if you go from manipulation to whatever speech recognition, you're going to see very different kind of preconditioned learning. At least it's not clear to me if you can even have those preconditions. But in this work, we focused on coming up with a planning approach. So whatever those variables are, whatever the model is, how do you solve that optimally?
Do you think it matters what the numbers are? That you really have to accurately estimate all those costs?
Well, if not accurately, then to an extent that you can come up with a good plan, right? So if you are trying to plan over long horizons, you can't really do that with a very inaccurate model, because if it's a very inaccurate model, if the numbers are not right, then you're better off just doing some sort of greedy strategy. And the planning approach like ours makes sense only if the model is reasonable, is not too inaccurate.
I think if it really depends on, quote, accurate estimation of costs, it's going to be doomed to failure. You're never going to get those estimates right.
Well, at least in the experiments that we did, we were able to get those estimates to a reasonable degree of correctness. And of course, it remains to be seen.
So what was the control?
Was that?
How did you know you got them to correctness?
Well, so when we train these precondition prediction model, so for example, if you get a demonstration next to wall 1, you would expect that the prediction model predicts that you can solve tasks which are next to wall 1. So these were more like qualitative results, and not some like hard bound on the accuracy.
Right, that's my point. If it doesn't work with qualitative results, it's probably not going to work.
Right. So it does. So my point is it does work with that. But
Yeah.
what I'm saying is that if those numbers are like not accurate at all, then you probably should not be planning at all.
So expanding on this idea of testing, basically, as I understood it, 99.999% of the testing was done in simulation. And there was one slide where you said, yeah, we did it. We did a real life test.
Right. So most of the evaluation that you see in this table, the results in this table are in simulation. And we did, I think, around 10 trials in the real world for 10 different sets of peg insertion tasks, where each set was around 10 tasks.
So given that actual real life testing is so hideously expensive, how would you test this thing on a much larger scale with thousands of tasks? And, I believe it was yesterday, I learned a new way to pit avocados. So there are a gazillion examples or tricks like that. How are you going to test it in that rich world?
I totally agree with you. Like even to test with the simplified domain was a lot of work, especially in the real world. You have to provide these demonstrations, and because it's like you're reasoning over a large number of tasks. So if you're reasoning over 100 tasks, you need to be ready to provide demonstrations at any point. So in that sense, like testing this approach in the real world, especially on a large scale, is at least quite difficult, and I don't have a good answer for that.
All righty. I guess my advice would be, if you were going to continue in this line, is that I would pay a lot of attention to what the language people are doing, because
All right.
they have all the same problems.
Gotcha. Yep, that's a good tip.
All right, thank you very much, Chris. Oliver, do you want to go next?
Sure. So Shivam, I was kind of thinking about, this, I guess, what Chris also mentioned, like, different kinds of inputs, different kinds of demonstrations as well. One kind of demonstration that's becoming increasingly popular is the idea of corrections, right? That you don't just give a one-shot thing, but that you rather have a smaller cost for applying corrections later on. I was just kind of wondering, how could you kind of, or is it possible to fit that kind of an approach into this framework?
So are these corrections applied to some demonstration that have already been provided, or?
So the robot is executing a task, and you're simply, during execution, moving it so that it's it's more accurate, effectively. So it's not as difficult as a full demonstration, but obviously you need to have a reasonably good starting point.
Right. So I mean, one easy place to start would be to just add it as a different action to our MDP. If I can go back to the MDP. Right. So if a correction is less cost than a demonstration, you can just add it to your one-step MDP, and it just does a different kind of a change to your skill library, right? So instead of adding a new skill to your library, it modifies an existing skill. So that's an easy way to add it to this MDP.
But if you sort of require that a certain amount of like success probability is likely, like it needs to be a certain quality of skill. I mean, it shouldn't just be a cheaper skill, right? Like a cheaper demonstration.
But so that can be enforced at the human level, right? So if I can assume that every time I ask for a correction, there is some quality control, which is that the resulting skill achieves whatever 0.9% success. Is that an assumption that I can make, or can I assume that the correction is going to be of good quality or not?
It's going to be of good quality, but you need to have like a certain p fail to be maximum 10%, for example.
Right. So can it be dealt with at the human level, or
what does that mean, to be dealt with at the human level?
So it means that if I ask for a correction, then I am guaranteed to get a skill which satisfies whatever 0.9% of success, 90% success.
Not necessarily, right?
So I mean, then you'll have to model what happens when a human corrects a skill, right? Because if the human after correction is not improving the skill, then is it valid to call it a correction? Right. I mean, I think it's a reasonable assumption to make that if we ask a human to correct a skill, the success probability is going to go up.
Okay. Another thing related to your future work, you mentioned this idea of sort of estimating the cost of a human demonstration from simulation. I feel like that's kind of making an assumption that like what's difficult for a human is difficult for, I guess, a planner or RL. Is that true?
I can imagine situations where this would not be true, but I can also imagine situations where it could be true. So it
Do you have
could
some
be.
examples? Yeah.
So for example, if you're using reinforcement learning to solve this task, right? There are a lot of potentially local optimum that the RL algorithm can get stuck in, whereas to a human, it's quite intuitive, right? So it's not going to be a lot more difficult for the human. So here it's not clear if the costs are going to transfer, right?
Okay. But do you have examples where it would transfer easily?
So, I mean, it's not immediately clear to me what that relationship is. And I think it also depends on how much information there already is in the RL algorithm or whatever algorithm that we're using to learn. Let's see. So for example, if you're using a motion planner to go from A to B, and let's say there's a lot of clutter, then if it takes a lot of time to find out a good plan, it's likely that there's a lot of clutter. And even for a human, it's going to be more work to come up with a good demonstration.
Okay. And I guess one more question from my side. So you're creating this threshold, right? You're automatically tuning that.
Right.
So like, what kind of thresholds did it end up with, like in your experiments, and is there sort of an interpretation of what that kind of means?
Yeah, sure. So let me go to that slide. Yeah, right. So typically, a good threshold is somewhere in the middle of the range. So it's not close to 0, it's not close to 1, because those kind of tend to like be rather extreme and lead to a lot of loss of information. So what I observed were like the best ones were around 0.4 to 0.7, somewhere between those two numbers.
Do you have like a interpretation? So if it's a 0.7 threshold, does that tell us something about this set of tasks, or?
I think I don't really have a good answer for that, but I can take a stab at it. I think that depends on the preconditioned model that we have, right? So sometimes when the models are trained, they predict very extreme values. They're very confident it's either 0 or 1. Sometimes it's kind of fuzzy, so they predict a lot of numbers which are not extreme. And the right threshold is basically dependent on what kind of predictions the model is making.
Okay.
Yeah.
All right. I'll leave it to Max.
All right, thanks, Oliver. So I'll ask just a few questions, and so that the audience also gets a chance to ask. One is, so you're kind of looking at the problem of getting AND tasks done as efficiently as possible with minimal cost possible, right?
Yep.
With the idea that potentially after those AND tasks are done, there will be a totally different set of tasks that will come in, and you'll need to kind of look at it again from scratch, so to speak. So in that type of setting, then given that the change, those set of tasks change over and over again, the preconditions model that you've learned may not be appropriate, right? So the question then is, how do you learn? How do you learn the precondition model for each one of those batches of AND tasks, kind of efficiently, so that you minimize the total cost? And related to this, do you need to look at it, that problem in terms of minimizing the total cost, which includes the cost of learning that model?
Right. So that's a good question. So far, I've assumed that the preconditioned model, it generalizes over the task distribution that is likely to be seen, which is represented by this task distribution F here. Now, the key challenge here is that you want to learn this preconditioned model in simulation because this requires you to, when you learn a skill, you want to evaluate it on a lot of tasks. and doing that on the real world would be rather expensive. So one possibility is that once you see those tasks that you need to do, and let's say you have a preconditioned model which does not work for that, you could do this training step before you start planning based on the tasks that you see. And however, it's not clear to me whether it would make sense to incorporate that in the cost framework, because like there is some cost to training this model, to getting it to make reasonable predictions. And if you don't have that reasonable predictions, then planning is not going to work. So even before you can plan, there is kind of like a fixed cost which you need to incur. Of course, this would be in simulation, so it is going to be much lower, but you need to incur that fixed cost to be able to plan.
Yeah. So, but I guess do you think there is a formulation where you can start out with almost like a no model and think and having a planning approach that reasons about whether you even need to build this model? Maybe you don't even need to build a model, right? Because the cost is non-trivial still, even in simulation. And then on top of it, you have a sim to real gap there, right?
Right. So, I mean, that's one of the future works that I talked about, which is you could do some sort of online planning with an imperfect prediction model. I mean, I can imagine you can do some sort of optimistic bound on the costs and use those optimistic bounds to guide planning. Yeah, that's one possibility. Yeah, but that's an interesting question. That's definitely on my mind for future work.
Okay. Second question I had was, so you kind of, once again, you're looking at solving those n tasks efficiently. Now imagine n goes to infinity, right? And it should somehow map onto the problem of what's the most efficient way to learn the skills, right? So how does it map on this?
Right. So if the number of tasks goes to infinity, then in that case every task is a good candidate to learn a skill on, right? And that basically becomes the active learning problem, where you can assume that you need to learn all the skills, and the question is, how do you learn those skills as quickly as possible?
Mm-hmm.
So in that case, you can just simplify this MDP, where you can kind of get rid of this human intervention part, because of course everything is reasonable. So you want to get a demonstration on all the reasonable all the relevant tasks. And in that situation, I think there are a lot of active learning based approaches which deal with this.
Yeah, but I guess my question is algorithmically, wouldn't it be the case that the set cover somehow, your approach would somehow be solving that problem for n going to infinity?
Right. Yeah. So right. So most of the active learning approaches are kind of greedy approaches, which minimize and maximize some number. So they can maximize they can maximize novelty, or they can minimize uncertainty in the robot's understanding of the tasks. Right. So you can think of the set cover approach as kind of trying to get to the optimal solution and not just the greedy solution.
Yeah.
So I can see how I can see that you could use the set cover approach to solve that problem optimally.
So what's the problem with doing that?
Well, there isn't really a problem. We could totally do that. The question is, how much it buys you.
So like solving it optimally versus
right. So yeah. Right. So there are certain situations in which a greedy solution will be suboptimal, but the question is how often those situations occur in practice.
Okay, sounds like an interesting experiment then. Okay, all right. I think at this point, let's see if the audience has any questions.
Yeah, I have. Shivam, if you go to slide 47, where you have the example, yeah. So when you showed this, I thought that if it's possible to learn some sort of transformation between tasks, then in this case, the robot needs to know that, all right, if I just flip left and right and up and down, I can use what I know for task A and solve task B. Do you think that that's possible, that you learn some sort of a transformation between tasks and apply it to some skills that you have learned in the past to solve new tasks?
I see. Right. So that actually is related to the problem of what's the representation of the skill that you're learning. So you can use a whole lot of different representations for solving this task, and each representation is going to have a different amount of generalization. So for example, if to solve this task, I used a fixed sequence of waypoints, that representation is not going to generalize at all. If instead I used a fixed sequence of actions, which kind of adapts to the location of the slot, that is then going to generalize a little better. And like you said, if you also allow for this transformation between the trajectories, then that's going to generalize a lot more. But of course, the question is, how expensive is it to come up with those transformations? And in this work, we assume that we have a fixed representation for the policy, and then we address the question, how do we minimize the number of human demonstrations? You could, of course, pick a different representation, and you could still ask the same question. So I feel like these two are kind of two orthogonal questions.
Okay, that makes sense. Thanks.
Any other questions from the audience? Or for that matter, from the committee, from anyone?
I have a question. I have one more question. So,
Yeah, go for it.
You're phrasing this as a set cover problem, and that kind of scares me because that's NP hard, right? And it's as Chris pointed out, you maybe eventually want to work with really large libraries, and you're using something that is computationally really difficult. And under the hood, you're not really solving set cover, right? Instead, you're solving a linear program, and then you're kind of rounding your answers, right? You don't actually, like, numerically, what's happening is you're not solving set cover, right? You're in fact getting not a hard assignment to each set, but a distribution over all sets, and then that gets rounded to give you the integer program. So if you actually uncover what's actually happening in the set cover, you get distribution over sets. Right? That's what the actual linear program is giving you. So I'm wondering if you could actually use that information, that you're not solving for a hard assignment to each set, but your solver actually gives you a distribution over sets, and actually use that information in your planning.
Right. So just one small correction, which is that the set cover problem assumes a hard set. It is not defined over a soft set. So we are actually solving the set cover problem using this integer program.
Well, the way most of these integer programs get solved is they set up as a linear program and then they round to integers afterwards. And so if you actually uncover the hood of what's probably happening when you're solving this, you're solving a linear program where the decision variables are not binary. In fact, you get distribution over sets, and then those get rounded. That's the common approach.
Yeah, so you're totally right. The standard approach is branch and bound, which relaxes some of these constraints and then solves it until it can give a solution which satisfies all the constraints. The good thing about that is that it still gives you the suboptimality bound on the solution. And most of the solvers that we looked at can handle millions of decision variables. So this is a problem which is really old, which has been looked by a lot of people. Hence, even though it is NP hard, there are very good solvers to solve this.
Sorry, I will check that. What I mean is, if you relax these from binary decision variables to continuous decision variables, and you get distributions over tasks, that's a much easier problem to solve because it's no longer an integer program. It's just a linear program.
I see.
And wouldn't relaxing these constraints, in fact, in the fact that you don't really care about set cover, you're going to continue using this task, wouldn't the extra information given by relaxing this to the integer program that's likely being solved, could you use that extra information in having continuous decision variables?
Yeah, that's a great point. Yeah, I agree that if we relax the decision variables to not be binary but continuous, that makes the problem easier, and you get this soft assignment, which is an easier problem. Yeah, I'll have to think about how useful that is in our case and whether that solves the exact problem that we are going after. For example, what does it mean to have zero point 0.7 of 0.7 as the decision variable for getting a human demonstration? So I suppose you're going to look at a probabilistic plan where you get some probability for asking for a demonstration or whatever.
Yeah, but you already have probabilities in all other parts of your problem formulation, both the MDP and in your preconditioning step. So I don't know if it would really hurt you to also look at what the probabilities here might mean.
Yeah, that's a very interesting suggestion. I'll think about it. Yeah.
All right, thank you. Yeah, that's my question.
Great, thank you very much. Okay, any last questions from anyone? I'm going to do a countdown to 3. 1, 2, 3. All right, the questioning is closed. So, Shivam, the committee got to talk. Everybody